Hi and welcome to the second video in the series of controlling and animating your layout with OpenLCB. So I've now done a little bit more work and I've put a couple more signals into here, and here you'll see the train is running the back and forth script, and I've added the signals into that script as well. So you'll see eventually the signal will go green and the train will start to run. Then as it passes through and it hits this spot detector here, the signal will change. And then here, obviously at the moment this signal is on red. Shortly the signal will go green and the train will be allowed to move back, just gone green now. So the train is now moving back again. Then as it gets to this spot detector here, the signal has gone red. And this script will run on and on and on, as I say. So I'm going to give you a little bit more insight into the electronics involved and show you some more and explain a little bit about the PC again to CAN bus, because I've got a little bit of news on that topic as well. So what I'm going to cover basically over the next couple of weeks is taking this section here, how I would go about to do the automation, what I'm doing here, and what kit I would have. Now, at the moment, when I set my layout up, I had my block detection all over here. But if you were doing yours and I was doing this again, I would run my DCC bus around the layout in the two wires and then take the droppers, and I would need 4 spot detectors for this section here. So 1, 2, 3, 4. Here I treat as 1 as part of the block here, sorry. So that's that covered. There is cuts in the tracks to suit that. So that would take up 4 of the 10 inputs, leaving me 6 for the spot detection. So in this case, I've done 1, 2, 3, 4, 5, 6 on this node here. So that's all the inputs. Now the signaling, what I've done here is these are TMC signals. They are common anodes. So this needs 6 outputs just for these 3 signals here, and that goes into the MCP 23017s. So, for a small cost, this is something you could use this for. Obviously, there's still a lot more pins available to us, but at the moment, that's how I would do it. I'm not using all of them pins because, as I say, my spot detection is on my node over here. So for my signaling, I'm using these now. I think when I bought these, they were about £4 each from TMC in the UK. They are common anodes. Now there's a bit of confusion sometimes when people work with these because you've got a red and a green and a black wire. The black wire we use to supply 3.3 volts. Now you could take the 3.3 volts from the shield. I personally wouldn't do that. I have a separate bus around for my 12 volts, 5 volts and 3.3 volts. And then the red and the green are used for grounding to turn the LEDs on. You can only have one LED lit at a time, and due to the current pass through of the LEDs, if you had them both grounded, the red LED would be on. So, for the price of these, it's not worth me even building or trying to 3D print my own. But hopefully, that's the type of thing. So with a number of these and these, you can see, and you've seen the script running. So previously, I've been running this MERG CAN-USB 4 for my PC, so JMRI to my CAN bus. And this, I personally think, is the way to go. Obviously, because I like soldering, but I am also going to be testing this one here. Now, I've had a quick test of it the other day, or yesterday actually, and I've just taken it off because I wanted to do some work on the code to try and get some more reliability and some minor changes to the sketch. So this is coming along nicely. It should be able to easily cope with this layout up here, but as I say, I'm not going to release the code until I'm really satisfied with it. So I think it's going to be, you know, a week or maybe 2 weeks for this to come through. But as I say, for me, the best approach really is either the SPROG LCC USB or the RR-CirKits version of it. But for those who are happy to trial with the ESP32s, if we can make it really reliable, you know, that becomes another option going forward. You know, so we're developing these things and making the layout more user-friendly. The sketches are still being worked. We're currently trying, I think it's 3 or 4 different types of ESP32s, and we may also look at the Arduino Nano R4 Minima as a candidate as well. We want to try and make sure that the things, this one here does not have a native USB. It uses a UART chip. We've got some that we're trying that have got native USB chips in them, but some at the moment, some of those react a bit strange. When you shut down JMRI, you have to restart the SP32. I don't think that's such a big issue myself, but we're trying to see if we can get around that problem. So when it comes to the commercial products, the first one I'm going to look at is the SPROG DCC offering, and they have here a website which you can use. Obviously MERG members can apply for a discount of 20, but when we look here you'll see we've got the LCC. So the bit I'm going to talk about now is the USB LCC, and this is a node in itself, so I'll go into a little bit more detail now. So here is a list of the features, and the important thing to note is obviously it's a USB interface for the NMRA, LCC and OpenLCB, and the fact that it has galvanic isolation between the USB and the LCC network. So this is there to protect your PC, you know, from any potential damage coming across. It also has 2 bicoloured status LEDs, which I will go into a little bit more detail. It's supported by JMRI. It also implements an LCC node. Now, so it's got the LCC bootloader for firmware upgrades, which is a nice, neat feature. And it has 2 configurable LED functions via the CDI. Obviously, because this is a commercial product, it comes with dual RJ45 network pass-through connectors for termination, and uses a standard FTDI driver included with Windows, Mac and Linux. Obviously, host side is USB powered and the network side is powered from the LCC bus. So when we look at this here on the end, you can see it's been marked up for USB activity, LCC power, LCC send and LCC receive. So the activity send and receive LEDs blink briefly for each message, and the send and receive LEDs illuminate for short periods at startup. So once you open the node in JMRI, you'll see you've got a number of segments that you can adjust yourself. Obviously you've got the usual backup and restore feature, which is a very handy feature within LCC and OpenLCB. So here you can see the LED configuration segments. So I'm not going to go into too much details on this. Obviously Andrew has an excellent user guide for this node, so that I think is one of the excellent solutions for people who do not want to get into DIY for LCC. So I'm going to talk about how to set up the spot detectors that I've shown. So when we scroll down to the inputs, so that's this section here, obviously these are set up as pull-up highs, so 3.3 volts. So you've got 2 choices, direct state tracking or push button toggle. We're going to use the direct. Now, as said it before, I do use a delay on these, and I normally set this one here, so off delay after transiting high, and I set that to 10. Click on right. Now the next thing I need to do is set up the sensors so that they work within JMRI. So when we open this section here, so I might give it a name. I use a name that will mean something to me, so I'll call it Spot 1. Then what I need to use, these, when they see a train, they go high, so they go 3.3 volts, and when they're inactive, no train, they're at low ground. So we need, so when we want the active, so we'll copy this from here and we put it into this one here, and then we want the low state to be this one here. Then the next thing we do is make a sensor. You'll see this appearing here. Now if you were doing the MERG block detectors, again here you do not need to use these two delays here because that has got a built-in delay already. So again, the ESP32 pin is at 3.3 volts. The pin on the ESP32 is high, and it only goes low when the train enters the block. So we need to make a new name here for the sensor. I'll go BL01, and then what we need to do, so when it goes low, we copy that and we paste it into the active. And this one here, we want to take the high state and paste it into this one, and again we make a sensor. Now if we go into the JMRI and we now look in Tools, Tables, Sensors, you'll see we've got two here. So one is saying it's inactive and one is saying it's active. This is because at the moment the block has got nothing in it and the spot has got a train over it. So that's how we set these bits up. But the important thing is to note the name here for when we use the scripting, which I'll show you in a second. Now I also do set up the LEDs, but I'll show that a little bit later on. So when I'm editing my sketches, I use Thonny, and the first thing we need to do is import this JRA and import JMRI. Then we have a class which is in my case called LCC test. I'll make this available on my GitHub repository as well, so people can see how I do it up there. But then we have a def init here, and these are the four sensors that I'm using for spots. Now I've called them slightly different here than what I've just shown in the video, because that was done on the fly just to show you. So that is them sensors there. Then the next thing I've got here is set self throttle, and the address of my little Ginty loco is 4, and then we have false, and that means the loco is going to move forward. So that is all the defining of the sensors. There is another way we can do that, which is just down here. So that is pre-set up, but what we can do, we can do it differently down here. So there's two ways, which really might seem confusing, but I'm showing you both just in case anyway. So the first thing we do, ignore the print statements, I don't really use that, but it's available while you're troubleshooting when you're setting your script up. So you'll see here I've got sensor.provide sensor, and then this is what I call my signal heads. So a signal head has two LEDs, a red and a green. So what I needed here is I first start off by setting signal head 1 red to inactive. So that's going to turn the red LED off. I've got this one here set to active. This is the signal that's in the what I call the siding to where the train's going. So in that case I just want the red LED to be on to make sure it is on in the actual script. Then I wait 500 milliseconds and I set the next sensor, which is for the signal head 1 green. Now you'll notice we're using sensors, not light, and this is what we found the easiest way of doing it, because a light has to have something to trigger it, so we just call them a sensor. And what you can see here, I'm setting the signal 1 to green by being active, and then I just make sure the throttle is set forward so it's true. I wait 1 second just to give it time to catch up, and then I tell to set the throttle for the Ginty at 0.5, so 50% throttle. The next thing I do is wait for the next sensor, so the one that will speed it up is S403, and that then sets the throttle speed to 0.8% or 80%. I then wait for the next spot detector, which is S4, and I set the throttle to a speed of 0.5, so 50% throttle. At this point here I want it to change the green LED, so I set that inactive and instantly set the signal head 1 red to active. I then move forward a little bit more, and I'm waiting now for the final sensor in the block, which is S407, and when I see that I set the throttle to 0. I then wait 8 seconds. I then set the sensor here, so signal head 6, which is the one in the siding, I set the red to inactive and instantly set the green to active. You could put a slight delay in that if you wish, just to make it look like the signalman's actually pressing the button or whatever. I then set the throttle into reverse, wait a second as we say to catch up. I then set the speed to 4, and then I wait for the next active sensor, which is S403, and at this point what I'm doing is changing the signal head number 6, so in the siding I turn the green off and the red on. I then wait for the final sensor, which is S402, and I've got a delay here just to give the train a little chance to get to the point that I want, because I'm going so slow, so I use a slight delay in the time before I set the throttle to stop. I then wait 8 seconds, and then we do a return, which makes it loop through this code repeatedly until I stop it. So what we'll do, we'll set up a button onto this screen. So we go Preferences, Startup, Add a script button, and we'll call it Shuttle. And we've got to tell it where we've got our Python file. So I've got it in my documents, JMRI scripts, and it's Dockland Shuttle. So we open, and it's in there, and we click OK. So what will happen, we click Save, it will restart. Do you want to save the tables? Yes, or you always want to make sure. So give it a name, we'll call it LCC, OK. So what you'll see now, we've got this button here. Now the other thing we can do here is we've got a thread monitor, so we click this and we can have that open. Then what will happen, we can click here. Now if I do this now, this isn't going to work because I haven't actually got all the sensors set up within JMRI. But what would happen, you would see this appear here. I'm actually working on my computer downstairs at the moment, not the one in the loft, but that's how you create this button. So at this stage I'm going to stop this video, and in the next video I'll do a bit more. As I say, if you could like and subscribe to the channel, that would be great. Obviously Please post any comments if you've got any questions, if you feel I've missed anything, and I will answer them in the next video as well. So anyway, thank you again for watching. Bye now.